Hi everybody, and welcome to D-Shape Construction 3D Printing Technology. This is a final presentation for CM4440, Advanced Construction Technologies. And this presentation is by group number 7, which includes Skylar Brasher, Abigail Mansfield, Evan Spurger, and Jacob Gamble. Let's jump right into it. Introduction to D-Shape. Let's talk about the inventor, founder, Enrico Dini, as pictured below to the right. He's a descendant of the Italian mathematician Ulisse Dini and son of famed Piaggio engineer Egisto Dini. D-Shape was first envisioned in 2004, the patent filed in 2005, and Dini founded the industry pioneering Monolite UK in 2006. The following year, 2007, Enrico printed the iconic Radiolaria Pavilion, the world's first 3D printed architectural structure. This marked a new era in construction technology. So Enrico would go on to showcase D-Shape's immense potential through a variety of visually stunning projects. I won't get too much into them because that'll be covered in a different section. But the applications are definitely varying, that you can use it in a variety of projects. For his pioneering work, Dini has received a plethora of awards. I'm not going to get into all of them, but I do want you to be able to see them. He is definitely critically acclaimed in the awards section. Today, Enrico continues breaking new ground across sectors. Again, I'm not going to get too much into that because it'll be in later sections, but I did want you to be able to see the founder, see the source where this actual technology was coming from. So actually getting into how this works, D-Shape is a groundbreaking 3D printing system that materializes buildings directly from digital models using a novel layering process. This technology works by depositing alternating layers of granular matter like sand or aggregate and specially formulated binding ink that fuses the grains together. This enables the printing of solid structures from the ground up, wall by wall, layer by layer. And if you look at the picture down to the right, this actually looks really similar to a non-commercial 3D printer, just at a larger scale. I know that it looks very similar to the Ender 3 that I have. It has an XYZ axis, trolley, extruder. It looks like the bed is wired. I know with an Ender it's heated. I'm not sure if that's how this would work in the same way. But it does look like the bed has a specific technology in it that keeps the product from sticking to the bed. Very similar, just looks scaled up and it uses different materials, but I think that is definitely the basis of where this is coming from, or this could be the basis of the non-commercial one, but very similar. While traditional 3D printers use tiny inkjet style binder jets, D-Shape's nozzles dispense small volume drops that rapidly bind large areas. This is due to the potency of the ink. You don't have to have a whole bunch of it for it to work well. Two robotic gantries work in sync, one precisely spreading each fresh layer of granular matter, so the sand and aggregate, the other following behind to print the binder patterns with the ink. D-Shape is multi-material. It's compatible with a wide variety of aggregates, fibers, and customizable binder chemistries. This just means that we can go in and use specificity to try and find the right fit for the right project. Say that we're wanting something as a specific kind of aggregate for the project that we're doing, we can actually specify, pull it out, and use what we're wanting. So this patented approach allows printing entire building structures in one seamless process. Complex shapes with fine details are no problem. This is due to the digital precision and design freedom. The printing progression is also self-supporting, removing the need for any temporary formwork. Again, going back to how non-commercial 3D printers work, I think this is very similar. So say that it's something that's hollow and needs supports from the inside. With a non-commercial 3D printer, it would actually print the supports and make them where they're breakable. It would add a seam where it breaks off. At this level, at this scale, I'm not sure that it would work exactly the same, but I'm assuming that it would work very similarly. Each component can be optimized for factors like strength, aesthetics, or sustainability. Again, going back to the variety of aggregates, fibers, and binder chemistries. Expert operators monitor the automated construction process for quality assurance.
In this section, we'll be discussing the advantages and disadvantages associated with D-Shape 3D printing. Beginning with the advantages, we have material efficiency, design freedom, speed, reduction in labor, environmental benefits, and virtually unlimited customization. And to elaborate on these, beginning with material efficiency, only the necessary material is used. There's no need for any form work or molds because the printing progression is self-supporting. In addition, it uses inexpensive natural materials such as sand or crushed stone, which can be optimized for strength, aesthetics, or sustainability. Another advantage is the design freedom and customization. As you can see in the picture below, complex shapes can be created with ease. This leaves opportunity for architects and designers to create forms that would likely be impossible or at least very expensive using traditional methods. Additionally, we have speed and reduction in labor. Along with the ability to create complex shapes and objects, large structures can be printed relatively quickly when compared against traditional masonry and concrete construction. Moreover, a single operator can operate the entire printing procedure, which requires significantly less manpower than traditional methods of concrete construction. Environmental benefits, such as reduction in material waste, less energy consumption, potential use for recycled materials, and less transportation impacts on the environment from carbon emissions, are another advantage of the D-Shape 3D printing process. Moving on to disadvantages, we have material limitations, size constraints, structural challenges, cost of technology, and regulatory barriers. With material limitations, this is a disadvantage because strength and durability depend on the binder and aggregate being used. Generally, this isn't as strong as traditional reinforced concrete, and this is due to the fact that there's no pre-mixing of the material and the liquid, which causes the components to bond differently than a typical concrete paste. So usually you'll have the dry materials mixed together and then a binding agent, whereas in typical concrete everything's all mixed together and it's all wet and creates a paste. So this is what causes it to not be as strong as traditional concrete. Size constraints. Although the printer is large, its size limits how big of a structure it can print. So modular construction would likely have to be the method if a large structure was being printed. This would be a great option for prefabricated items such as wall panels or any sort of prefabricated thing where you could print it off-site and have it shipped to the job site to be put together modularly. Additionally, we have structural challenges. Complex structures will also need to have reinforcement, i.e. rebar, which is not something that is easily integrated into the 3D printing process. There can also be issues with adhesion of the layers. Delamination can occur, which can reduce the overall strength. There's also some fragility during the printing process while the material cures and hardens. Lastly, we have the cost of the technology and regulatory barriers. These printers are not cheap, very expensive upfront costs and the operational costs for the printer. These costs include software costs, skilled labor costs because it takes a special person to understand how to actually operate this machinery, maintenance and downtime. Downtime, especially when it runs out of material and you need to load more into it. Setup and calibration, all of this takes time and there's costs associated with that time. Regulatory barriers can cause issues because there are very few established standards which can make getting permits and insurance difficult. Pilot projects often have to get special exemptions, i.e. experimental construction permits, in order to be able to use something like this.
There are a few applications of D-Shape 3D printing that will be discussed. The first being a collaboration between D-Shape and Trinale Milano in 2010. In this collaboration, they printed the world's first house that was entirely 3D printed in a single process. This house was called Una Casa Tutta di un Pezzo. As you can see from the photo in the lower corner, there was 4 walls and a roof constructed on this house, along with a few window openings. It was 2.4 meters by 4 meters and included a bathroom, a kitchen, and a bedroom. And construction from start to finish took about 3 weeks. If you remember this slide coming up on some future slides, you'll be able to see how this technology has progressed over the years and how it has continued to speed up the construction process. This application demonstrates the potential of 3D printing for a rapid, efficient housing solution. It also highlights the ability to produce complete structures in a single and uninterrupted process. Another application helps to highlight the sustainability aspect of this printing process, especially in urban settings. A study was published in the Journal of Cleaner Production, which explored the application of D-shaped 3D printing in constructing a fiber-reinforced footbridge to emphasize sustainability. In order to emphasize sustainability, they used the D-shaped technology as it enables a precise material placement to minimize waste. It also allowed them to produce a high comprehensive strength to enhance the durability by reducing the tensile stress to be resisted through the fiber reinforcement. A few of the implications this specific application has for D-shaped construction is that it shows the potential to revolutionize infrastructure projects by combining sustainability with structural integrity. And it also opens avenues for eco-friendly construction practices in urban development. As mentioned earlier, there are a few emerging global application cases that help to kind of show how this technology has progressed over the years and how it has continued to speed up the construction process. One example of this is in 2016, there was a multi-story building 3D printed in Shanghai by Winsun, and this building was then later assembled in Dubai for use at the Museum of the Future. This structure was 242 square meters, which if you think back to the initial house that was built, that was about 8 meters squared, and it was printed in 17 days and then later assembled in 2. That initial house took 3 weeks to build, and this took 17 days, so a significantly larger structure was printed in less time, only 6 years after this technology was used to build the first home. The cost for this structure was $140,000. It did cut the labor cost by 80%, and the material waste was reduced by 60%. Again, this is why it was used in the footbridge example to help increase the sustainability of construction. There was also an earthquake-resistant house built in China. This house was 400 meters squared, and it was built in 1.5 months. So for nearly double the size of the multi-structure building in Shanghai, and in twice the time you have a structure built. Both of these examples help to highlight the flexibility, cost efficiency, and speed of 3D printing and construction. Not only that, but again, they help to highlight the sustainability aspect of this technology and how it can help reduce material waste through that precise material placement.
Contour crafting refers to a special form of 3D concrete printing. In this process, an extruder nozzle attached to a Ganny crane is used to apply a concrete mixture. The crane or extruder nozzle travels along a digital floor plane of the building object and pieces layers of concrete on top of one another. The term contour crafting is trademarked by the Contour Crafting Corporation, which was founded by Mr. Koshevitz. The company began researching direct concrete 3D printing using extruders in 2008, which led to other leading manufacturers in the concrete formwork industry to begin developing such forms of 3D printing. Contour crafting has a lot of benefits for architecture, allowing companies to print buildings or any infrastructures directly on place. It can become a common method to help in building construction for people in need, like houses or buildings, especially after traumatic events. These machines are capable of printing in any urban setting or any infrastructure setting as well. As printing projects is one advantage, it also allows us to create more complex designs not capable with traditional construction methods. Although there have been some improvements in developing and implementing large-scale 3D printers in the construction industry since earlier attempts, the extrusion-based method still confronts a number of challenges. Such challenges mainly are caused by limited material performance of concrete. Concrete, used in extrusion-based technologies, is in its early stages of development and does have promising potential of improvement, but does not yet have comparable consistency and viscoelasticity property usually exhibited in polymer materials. This issue is due to the fact that material needs to go through a liquid stage and hydration process to be solidified for successful self-supporting. Such large thickness of concrete filament may serve its purpose of expediting printing speed, but limitations in material level, as mentioned, are what really limit the thickness of concrete filament. Low resolution of 3D printed parts is also what limits the application of extrusion-based technology. The gaps in between 3D printing and the other building components, such as mechanical, electrical, and plumbing, are not necessarily required to be filled out, but certain joint systems are required to overcome compatibility issues. A dedicated joint system utilizing other means of 3D printing technologies is to either be integrated during the printing process or post-integration via the construction process. These methods could be used as an alternate solution. Current research into the extrusion-based process is mainly focused on advancements in process competence aiming to achieve improved performance from the printed components, extension of material availability to increase system integration in extrusion-based processes, numerical analysis to analyze and predict the physical properties of materials, and modeling and simulations of the dependence of material performing on designs and printing strategies. Thanks to the recent developments in digital technologies, the potential and performance of extrusion-based technologies is expected to increase. Such developments assist extrusion-based technologies are anticipated to increase the suitability both of the technology and of the materials, extending the areas of application of this technology and enabling a quality of printed parts that is comparable to that of conventional construction methods. The contribution of machine learning to an extrusion-based extends to the control of process parameters and print positioning, predicting a cost and energy consumption and process monitoring. Machine learning technology has great potential to overcome this complexity, enabling a more reliable prediction of energy consumption and cost on extrusion-based manufacturing.